Welcome everybody to the Fractional Calculus Seminar Series. Today we have Professor Nikolai Leonenko, who is a professor at Cardiff University since 2006. He joined Cardiff University in 2000. Before he was a full professor of Kiev National Taras Shevchenko University, Ukraine, and also had some visiting position in Case Western Reserve University, Cleveland, Ohio, and Queensland University of Technology, Brisbane, Australia. His selected honors include K.N. Krylov Medal of Academy of Science of Ukraine in 1993, the highest annual award for mathematicians in Ukraine. His Google Scholar citations include 6,952 with an H index of 38 and an I index of 138. His citation on Maths SciNet is 1,500. He published 285 papers and 2 books. His collaborators include O.E. Brandanov Nelson, C. Hyde, M. Taku, Mark Meerschaert, M. Mersbach, N.R. Sheikh, V. Han, F. Avram, M.D. Rius Medina, I. Padlubny, J. Vaz, Ivan Nordin, amongst many others. Is the member of the editorial board of 5 international journals. In particular, he is the deputy editor-in-chief for the Journal of Theory of Probability and Mathematical Statistics, and the member of the editorial board of the Fractional Calculus and Applied Analysis. Uh, his graduate students he has advised over 19 scientists who have received a PhD in probability theory and mathematical statistics. They work at different universities of USA, Australia, Italy, Israel, Uzbekistan, with Vietnam, Poland, Ukraine, Croatia, and Egypt. Is currently advising 6 PhD students at Cardiff University. Professor Leonenko participated in the program for fractional differential equations held in January to April 2022, and in the program of uncertainty quantification and modeling of material program held in August 2023 at the Isaac Newton Institute of Mathematical Sciences in Cambridge. Professor Leonenko also participated in the program of stochastic system for anomalous diffusion, also held at the Isaac Newton Institute of Mathematical Sciences. It's a pleasure to have you, Professor Leonenko. You may please begin your talk.
Okay, Pavan, thank you very much first for invitation me to give a talk on the series of seminars. And the title of my talk is Fractional Hyperbolic Equation on Sphere with Random Data. Basically, I will talk about so-called random differential equation. It means that we have to consider a differential equation of basically telegraph type or fractional hyperbolic diffusion type. And randomness is going from initial data, initial conditions. The first part is joint work with Jaime Vaz from Unicamp, Brazil. And the first is, let me introduce a kind of my basic notation and what is known under the name of spherical random fields. Okay, so consider sphere in three-dimensional Euclidean space S2, which is defined as a set of all points in R3 such that norm of x is equal to 1, so radius is equal to 1. And also we denote Lebesgue measure or area elements on the sphere as sigma d theta d phi, which means that this is sine theta d theta d phi. So theta and 5 are from 0 to pi, and from 0 to pi it's Euler angle. And basically we are considering now spherical random fields on complete probability space denoted by T. And in this case, this function of space of elementary events, omega, and also the another coordinate is belongs to the sphere. So basically it's a map. This fields maps omega times S2, which is defined into R1. It means that this is function on a sphere. So if we consider the stochastic process xt, sum xt, then it means that time t is now replaced into the elements on the sphere. So that is why we have theta phi instead of t. And also, of course, functions in Euclidean coordinates and spherical coordinates usually different. So to distinguish, we will use t with tilde when we use Euclidean coordinates. We can use it for this, or t of theta phi without tilde if we use spherical coordinates. So if without tilde, it means that we are using a representation of functions or random fields in spherical coordinates. Otherwise, if we use with tilde, it means that we are considering Euclidean x. So basically, again, spherical random fields is a random function or on a sphere. So it means that for any omega, t of theta omega or t of x is a random variable. So random variable. Okay, and that's our object of interest. And basically now we are going to define what we mean under the isotropy of these random fields. So the field tilde of x, it means that we consider it here Euclidean coordinates, is called isotropic in a weak sense on the sphere S2 if the second moment is finite, and the first and the second moment are invariant with respect to group SO3 of rotation in R3. So it means that these two conditions hold, that expectation is the first moment is the same as expectation if you consider apply the element of group to rotate x, and the same for covariance function. If you put here this rotation of x and y, you have expectation of t of x, t of y for every rotation and for any x and y of c. So, well, I mean, for a spherical and random fields, probably the best reference in modern literature is a book of Domenico Marinucci and Giovanni Peccati called Spherical Random Fields. This book is published maybe 5 or 7 years ago, but still the best book in this area, and I would recommend people who are studying this subject just to refer to this book. So probably it's a time to refer to this book. Even this notation and this definition are known in other books, and maybe historical, I even don't remember who was the first who introduced this condition. So again, in three-dimensional space, we have a group of shifts and group of rotation. And now we consider an invariant of the random fields, the first two moments in the group of rotation. So it is easy to see that this is equivalent to say that expectation of this random field is a constant. Without loss of generality, we always assume that c equals to 0. And covariance function, expectation of t of x, t of y, or in spherical coordinates, expectation of t of theta phi, theta prime y, t of theta prime y, depends only on the angular distance between 2 points, P and Q. P is a point with spherical coordinates theta phi, and Q is with spherical coordinates theta prime, phi prime. And if you consider angular distance between these 2 points on the sphere, then it means that covariance function depends only on the function of this angular distance. It's easy to see. And basically, after that, we will use so-called spherical, assume something very natural about this random field, like mean square continuous, for instance, and measurability, or there are different assumptions for this. Basically, that's enough, probably mean square continuous and measurability. And basically, in that case, we have expansion of this random field into the spherical, into the so-called Laplace series. Laplace series is defined as some random coefficients, ALM, and YLM of theta phi, which are simply represents complex spherical harmonics. Complex spherical harmonics are simply orthogonal functions on a sphere. So basically, that's a typical Hilbert space expansion, yes, because of we can consider some orthogonal function on the sphere, and then coefficients of this expansion, which are defined later on, but in this case they are random, but potentially if this is simply function on the sphere, we can use this expansion, which is known as Laplace series. And again, for all our lecture, YLM of theta phi is spherical harmonics, orthogonal function on a sphere, and about RLM, I will define them later on. But again, basically, we can view, there are several views on this so-called spectral representation of spherical random fields. Either this is Karunen law expansion, which is converged in the Hilbert space of L2 times S2 and with Lebesgue measure on the sphere. It means that if you consider truncation L from 0 not to infinity but to L, and then if L goes to infinity, in mean square, we have such a convergence with a weight which is Lebesgue measure on a sphere. And also, one can interpret this as, in another sense, according to Peter Weyl theorem, the expansion holds in Hilbert space L2 of omega for every x. That is, for every x, we have almost sure such conversions. Again, for us, maybe the first, probably more traditional interpretation via Karunen law and law expansion. And well, for us, it's enough. But again, it's not. Again, this series in general, series of expansion function on a sphere, known as Laplace series. And on the other hand, this is typical spectral representation of the random field, since spectral representation depends on the group of which are group of invariants, and in this case, I mean finite dimensional distribution invariance with respect to some group, and then basically for a sphere, of course, the Laplacian, if you consider eigenvalue problem, the Laplace for eigenvalues, we obtain that spectre is discrete one, and that is why instead of integrals, typical integrals in for a stationary processes, we have a discrete series, which is known, as I said, as Laplace series. Well, of course, for most of participants of the seminar, this is known, but I assume that there are some people who are first time. That is why I'm a little bit detailed. So again, now about orthogonal functions. Orthogonal functions, again, we use this wave YLM of x if we consider a function on in Euclidean coordinates, and without waves as if we considered expansion in spherical coordinates. And at least in spherical coordinates, we have such representation. So DLM, some normalizing coefficients, because of these functions are not only orthogonal but also normal, and e to the power em phi, and here is PLM of cos theta, which is denoted as associated Legendre function with index LMM, and PLM are defined as Rodriguez formula. And yes, I mean, we can define say as a Rodriguez formula, or again, this in this function we have such a function of, okay, because of kind of, okay, this is typical formula from classical orthogonal polynomials. But again, what is important for us is that we have system of orthogonal functions also normal on the sphere and YLM, and we can use them for expansions, for investigation, and so on. So again, orthogonality of these functions, because of their complex value, means that we have to consider YLM conjugate, and without conjugate, this is Lebesgue measure on the sphere. We have just a delta of L prime, delta of ML prime, and there are some symmetry property of these orthogonal functions, like with conjugate LMM start is -1 to the power ML minus sum of n. There are some other symmetric property, and that's examples of the spherical harmonics when in all this formula delta L prime is connector delta, and symbol star means complex conjugate. Okay, now it's a time to define the random coefficients. In accordance to general theory of Hilbert space, if we have a basis to expand the function, we need to multiply this function, in this case t of theta phi, into this basis, and that's the coefficient of expansion. In this case, because of theta and phi belongs to the sphere, in spherical coordinates we have such an integration, and because of t of theta phi is a random field, depends on omega, basically ILM is a sequence of random variables. So basically it says sequence of random variables which depends on two parameter LMM, and if t is a real value, that we have some, again, symmetry property of this expansion. And what is for us very important now, that if you consider now expectation of R, Lm, R star, L prime, N prime, you remember that this is kind of a random field with discrete parameters, L and M. Then we have a Kronecker delta function and CL, some function of CL. And this function is CL in this part of the theory called angular spectrum of isotropic random field. So CL is simply sequence of random variable, and so it's a sequence, not random sequence, because here expectation with some property we will discuss later on, and this basically plays a role of spectral density for stationary random fields. We have spectral density, and that's analog of the spectral density for isotropic random fields on the sphere, and that's denoted CL. CL now. Okay, that's the definition of CL, another definition. So in the other words, CL is a sequence, is a real valued sequence. And this real valued sequence satisfies this condition, so it's not arbitrary sequence. Again, as I said, for covariance function gamma of cos theta, which is expectation of t of theta phi, t prime of theta phi prime, we have this representation. Again, this is Legendre functions, and CL is a angular spectrum. So analog of spectral density of stationary process is CL now. It's simply sequence with, it's not arbitrary sequence, we need some conditions to have L2 conversions of all objects. And as I said, that's our main definition for today's lectures, because we will compute to the end the angular spectrum of some objects, which I will define later on. C0, C1, C2, Cl are called angular spectrum of isotropic random fields T of theta phi. So if you have some other parameters like time, of course, this will be function of time as well. So if T of theta phi is isotropic Gaussian field, so far we didn't assume anything about distributions. Then coefficients RLM are complex valued Gaussian random variable with such a property that expectation of RLM are equal to 0 and expectation of RLM times I star L prime N prime is delta coefficient CL, and CL is again is a angular spectrum or some sequence which satisfies this condition. So basically, for those who know this topic of CMB data from astrophysics, this famous picture of in Wikipedia or internet elsewhere of density, what we know about our history of our universe, simply it's angular spectrum, or angular spectrum of CMB, and that's basically we know CL. In the simplest case, of course, in reality, fields is complex, I mean tensor valued and so on, but the one component of this tensor valued field is isotropic, so-called temperature component, and in this case, you can see this CL for astrophysics in the internet, and that's famous picture. I will show it later on. But again, now it's a time to go to fractional calculus. So far it was random fields. Basically, I will use, I'm not sure that spherical random fields is it's a well-known object for most of the people on this seminar, but at least for some of them, I'm sure that it is. But now it's a time to go to fractional calculus, and I will use Caputo or Caputo-Chebashian derivative, and they are defined as for a function phi of theta, phi and t. Now it's a time appears and this is fraction in time Caputo derivatives, and they are defined in standard form. So I mean that the only difference is now you have some extra parameters theta and phi, because of if function depends on time, we can apply Caputo type derivatives of this. And again, if m is integer, we of course arrive to the classical derivative of function, and at least this is well known in this audience. So now let us consider the solution of the random source spherical fractional hyperbolic diffusion equation. So basically, so now there is no randomness here. Randomness will be later on. We consider the following equation. So 1 over 6 squared is a constant. Then the second, the derivative of the order 2 alpha um, for a time. Then 1 over d, the derivative of order alpha over t in the left-hand side. And in the right-hand side is ordinary Laplacian on the sphere. So alpha in this case between 0 and 1. So basically the second derivative is from 1 to 2. The first derivative from 0 to 1. And then we consider this non-random equations. So this is simply just classical, well, there are several names of this equation. We use a name of hyperbolic diffusion equation because of here there is a parabolic part if alpha equal 1, for instance. We have second derivative, the first derivative. The first derivative is kind of parabolic type behavior, and the second derivative is kind of hyperbolic if there is no first term. So basically it means that it's this equation has both parabolic and hyperbolic type behavior, and basically that is why we called fractional hyperbolic diffusion. Diffusion is kind of parabolic object, hyperbolic because of the second derivative. And again, there is a second name is in the physical literature of this equation, so-called telegraph equation. So telegraph equation, if we have one-dimensional case, and also in one-dimensional case, there are books about this. Basically, if you consider the second derivative with respect to time and plus first derivative with respect to time, in the right-hand side, let's say some sort of Laplacian or second derivative in x, in space. And so this is in time, this is in space. In this space is simply element of the sphere. This equation is known as the telegraph equation, and at least in Italian probabilistic schools, there are many people who studied this equation, starting from Enzo Singer and many others, Bruno Toalda and Mirko Davidio and many, many others. Okay, Luisa Begin and so maybe begin. Okay. So then to this equation, we will consider kind of initial conditions like the first derivative is equal to 0, but the first one corresponds to the delta function, which is source initial condition. And this is if alpha between 1 and 2, and then we have considered this type of kind of conditions which are typical for a sphere. And again, in the right-hand side is simply Laplacian on the sphere, and which is known under the name of Laplace-Beltrami operator on the sphere. So this is, form of this operator in spherical coordinates, which we'll use in computations. But again, this is standard notation and standard things in analysis. Okay, as I said, that if you consider fractional Laplacian and we consider eigenvalue problem on this sphere, then this eigenvalue problem with fractional Laplacian has a very clear and explicit solution. And eigenvalues are L plus 1 in our notation, and eigenfunctions are spherical harmonics. Basically, of course, it's one way to get orthogonal basis goes through eigenvalue problem, and in this case, it's spherical harmonics. That is why it's natural to look on the solution of this equation, which we consider it as generalization of telegraph equation on a sphere or whatever hyperbolic diffusion. It's natural to look in this form. So in this BLM of t are unknown coefficients and VA LMT are orthogonal bases. And then these coefficients are, of course, as usual, is a product of functions which are expanding in Laplace series n times into the orthogonal basis on the sphere. So that's a kind of standard notation. And basically, well, again, we have to introduce Mehta-Klaffer function with two parameters, alpha, beta, which is on this audience well known. And again, if beta equal 1, this is one parametric Mehta-Klaffer function. And if you introduce some sort of sets, omega, it's a special sets for which L less than A and plus I. And again, is a sets when L larger than A is missing here condition. Then basically this A is some sort of given explicitly here, and I is indicator function. We are able to, if you also introduce Z plus minus, which is minus C squared over D, these coefficients from equation T to the power alpha, over 2. You remember alpha between 0 and 1 plus minus omega. Omega is defined as y indicator. The first part when a less than a, the second where a is larger than a is missing a little bit here indicator, but because of the probably, but here is times indicator of a larger than a. And basically, if you also consider function BRL of t1, BRL of t2, which are a combination of these Mehta-Clauser functions with one parameter in points z with minus L alpha of t and z with plus alpha of t. Basically, again, this is typical for this series Z. We can find the fundamental solution or green function of this fractional hyperbolic diffusion point source initial value problem, and it is given by explicitly by this formula. So again, PL are functions from spectral representation of random fields in form, and FL alpha were defined in this form, and these coefficients from spectral representation. Basically, this is exact solution, if you like, fractional hyperbolic diffusion point source initial value problem, and which has maybe some independent interest. Well, this is partial cases when alpha equal 1, and we arrive to the famous formula which is known in the literature. In this case, Mehta function is exponent. We arrive to this formula. Again, you can see that indicator a larger than a less than a, and larger than a. And again, in this case, this is more similar to, for people familiar with telegraph equations, this is more close to what we know about solution of the telegraph equation. And again, this is partial case of the solution of our equation when we have a non-fractional case. So in this case, alpha equal to 1, and we can simplify a lot of formula, and we obtain an explicit solution of the or grid function of the telegraph equation of sphere, if you like, in explicit form. Again, when alpha equal 1, there is no there is no Mehta-Clauser functions, and we have the solution which is consistent with known formula. Okay, there are some other partial case which is given here for alpha equal half, but let me omit these details because of it's not important for us. And now let us consider the random fields, which are solution of the above hyperbolic parabolic diffusion equation. But now, if t equals 0, we have not delta function, well, not source initial condition, but initial condition is spherical random field. So T of theta phi is spherical random fields, and it means that we know coefficients ALM. And again, we assume something about initial conditions, and basically now the solution which was considered before is a random fields. And the random is introduced through Gaussian isotropic random fields at time t equals 0. If t equals 0, we have a simply object we already considered. So basically, and again, this is the same notation, spherical harmonics and so on. And the second result, which we present here, that basically the angular spectrum of isotropic Gaussian fields, that now it's a random fields, with initial value 28, 30, which was exactly was defined, and then a random solution of initial value problem of telegraph equation with random initial condition is given in form of the series, and in which YLM are still spherical harmonics, and now psi LM of alpha are stochastic processes which are given by the following formula. ILM is the coefficients of the expansion, random coefficients of expansion of our initial value problem, initial condition, and multiplying into function FL alpha of t, which was defined before, and in non-random case. So basically, we have such a representation of solution of the random initial value problem, when again, we have an initial condition random fields, and spherical, the equation is still the same as we considered at the beginning. So this is equation. So now we consider this hyperbolic diffusion or telegraph equation, and random initial condition P of theta phi if t equals 0 is a random fields, and the solution is given by this formula. So explicitly, and we can find covariance function of the solution, and from here we can compute the angular spectrum, because of covariance function is still the same as for any isotropic random fields, but angular spectrum CL multiplying into L alpha of t, FL alpha of t prime. Now everything depends on time. As I said, angular spectrum is a function of time, and here we can see explicit expressions for angular spectrum of this case. Okay, if alpha equal 1, we arrive to the more simple formula, and again, in this case, initial condition is random, and we have such a representation of initial condition. And again, covariance function is given explicitly, and yes, and this is given in this, well, complicated but explicit form, in form of the angular spectrum, Legendre function, and this function ILM and barium, which were already introduced. Remember, meta-cluster functions with some points from non-random initial conditions. Okay, here again some partial cases, and basically that's the end of the first part of our talk, which is exactly half an hour. And again, let me summarize that. We considered in the first part of the talk telegraph equation or hyperbolic diffusion equation on the sphere. And initial condition was isotropic random fields, Gaussian random fields on the sphere with given angular spectrum. And then we know the solution of this random field explicit solution. Sorry, where it is. Yes, sorry, some miss here. Yes, explicit solution of this explicit, absolutely, because all this function f1 alpha of t was defined before, and basically the stochastic processes, if you like, and we know the covariance function and spectral angular spectrum of these random fields. Okay, the second part is joint work with, again, Jaime Vaz from Unicamp, Brazil, and with Andrei Leonenko from Melbourne, from La Trobe, University of Melbourne, Australia. Okay, let us consider kind of more general equations, like now instead of 2 alpha, we have here alpha plus beta, the second derivative in time, fractional derivative in time, and here is again a derivative of order alpha plus beta, and here derivative of order alpha. So basically, if alpha between 0 and 1, and alpha from beta from 1 to 2, we have more general generalization of operator from telegraph equation. You remember in telegraph equation, the first derivative in time, the second derivative is d squared in time, and there is a first derivative in time, d over dt. But now the second derivative in time is generalized to order alpha plus beta between 1 and 2, and the first derivative is d of order alpha between 0 and 1. And now let us consider this equation in full space, not on the sphere. Later on, we consider a restriction on the sphere, but so far, this is equation in three-dimensional space. So again, R3 is three-dimensional Euclidean space, K square is coefficients, and delta is still some just Laplacian, classical Laplacian inertia. And again, we consider now initial conditions are random, and at time equals 0, this random, we have theta of x, which is, I will define later, it's random fields, function of x and also from omega, and initial condition in time is equal to 0. So basically, again, eta of theta is defined as random fields, which are homogeneous and isotropic in space. So if you consider a sphere, the natural group of movement is rotations. But if you consider random fields eta of x in three-dimensional space, of course, we can consider both space and rotation. And basically, now we assume that eta of x is a field which is homogeneous and isotropic with zero mean and covariance function. In this case, covariance function of this random field depends only on the Euclidean distance between x and y. This is well known. If fields is invariant with respect to both shift and rotation, that is covariance function is a function of Euclidean distance. And for a future, we will consider then restriction of this random field on the sphere, which will be consist of subclass isotropic random field on the sphere, and in this subclass we will find exact angular spectrum, and then to compare with the spectrum which is given in for CMB data. That's our plan for the future. But so far we have just a hyperbolic diffusion equation, or if you like, telegraph equation, fractional telegraph equation on in three-dimensional space. So in three-dimensional space, and with random initial condition is again eta of x is homogeneous and isotropic random fields. So again, I use some elements of the spectral theory of random fields. It's well known that a correlation function of this homogeneous and isotropic random fields is defined in this form, and this measure is called a spectral measure in three-dimensional space, or this measure is called isotropic spectral measure in probability theory or theory of random fields. And basically that's a spectral representation. It goes from some elements of spectral theory. And let us consider that if Q of xt is a fundamental solution or green function of initial value problem 36 and 14, so it means that we consider this initial value problem with source initial condition. That's a called green function. And if we consider now Fourier transform of this green function, h of k t, k is a parameter of the Fourier transform, and basically what is good in the series, but basically inversion of the, I mean, it's more easy to find Fourier transform of the green function than green function itself, and most technical difficulties are inversion problem from green function to from Fourier transform to green function. But in this case, actually, we can use we can express solution of this equation in form of the Fourier transform of the green function. Again, we need three-dimensional, three-parametric Mehta-Clauser function. In this audience, it's well known that there is a, b, and zeta parameters of Mehta-Clauser function. And again, if b equal 1 and zeta equal 1, we have one parametric, which is already used Mehta-Clauser function. And the first result is that we can explicitly compute Fourier transform of the green function of this initial value problem explicitly in form of the series with three-parametric Mehta-Clauser functions. This is pure analytical problem given in complex analysis, if you like. But basically, what is nice that we have explicit form of this green function. And well, that's one of the representation of this green function, which is, you can recognize here Fourier images of Laplace and Fourier images of equation. Well, okay, there are some simplification for some cases. Let me omit it. And now theorem 2. Theorem 2 is the following. Suppose that this Fourier transforms satisfies this condition. You remember, J is the spectral measure of initial condition. So if you know initial condition, we know J. So we can also find J for which this is finite. And then basically the solution of the initial value problem can be written as stochastic integral. And in this stochastic integral, Z is a random measure from spectral representation of random fields, initial conditions, and H, K theta is, so this is random measure, randomness is now everything is here. This is Fourier exponent, and H of kt is not green function, but Fourier transform of this green function. So, and then covariance function is given by this formula. Again, F is a spectral measure of initial condition. So we assume that initial condition is kind of known, and from equation, all equation now in this function H of k theta is nothing else but Fourier transform of the green function. Of course, all information about equation in green function, but that's a Fourier transform, which is the same. But of course, as I said, inversion is most difficult analytical problem. Okay, now let us consider. Yes, this is explanation of spectral theory of random fields, so-called additional theorem, Karunen theorem. Let me admit details. It's kind of, yes, I mean, I still have 10, 15 minutes. Okay, that's the element of the spectral theory of random fields, and they are kind of standard for this theory, and I will omit them. Maybe important that basically for a homogeneous and isotropic random fields, we have such a spectral representation. So basically, here is again spherical harmonics, and here is Bessel functions of order L plus half over mu t, and here is spectral random spectral measure. So everything is now non-random. The only spectral measure in this Z of Lm, which is defined from initial condition. So from initial condition, we have these spectral coefficients Z Lm of d mu, and the rest is from the spectral theory or from Fourier theory. Here there is a Bessel function of the first order, and also spherical harmonics. Okay, basically that's a spectral representation of the homogeneous and isotropic random field in three-dimensional space. Fields not only isotropic but homogeneous and isotropic. I is a radius, it's polar coordinate, and here is everything is given explicitly because of Z of Lm are random coefficients. Okay, now it's again here in these slides we have kind of a repetition of the definition of what is isotropic fields on the sphere. So basically, now let us consider spatial temporal random field. Now t is a function not of x, also on time, as it was before. And we assume that we have isotropy with respect to rotation in three-dimensional space. So J is the element of the group SO3, so rotation in three-dimensional space. And it means that the coefficients depends only on the distance between angular distance between these points. So this is the same definition which was on the first or second slide, but now there is a time because everything depends on time. And then again we have the same Laplace series representation. There is orthogonal spherical harmonics here of this series Lm, and now these coefficients now are coefficients of time. So it was denoted ALM, but now they are function of time, GLM of time, because everything depends on time. And these coefficients, of course, defined as typical for any Hilbert space. We have to consider, in this case, random function, but also non-random is the same, multiplying into orthogonal basis, which is in this complex values, that is why we have conjugate, and Lebesgue measure on the sphere. And again, if you consider variance or covariance function of this GLM coefficients in this spectral representation, this function CLM on T prime is called angular spectrum on these random fields. So again, this is the same representation of covariance function in form of the Legendre functions, and here in this representation for a covariance structure, CL is a spectral angular spectrum of spherical random fields. And that's a covariance function, which is given using the so-called addition theorem from a Bessel function. We can arrive to this function. Okay, so using so-called Karunen theorem, I will not formulate it here, but specialists in spectral theory of random fields know this fundamental result. Basically, we can represent now a solution of the initial area problem in form of the following series. You remember that Q of xt is a solution of telegraph equation with random initial condition. And random initial condition was homogeneous and isotropic random fields in three-dimensional space. So all random is now here. H mu t is a Fourier image of Green function, Fourier transformed Green function, and that's element of the spectral theory, Bessel functions, and spherical harmonics. So basically, now we arrive to the very fundamental result, which is known in the spectral theory of random fields. The restriction of the homogeneous and isotropic random field on the sphere is isotropic spherical random fields. So we denote is SFHDRAF. So it means that spherical fractional hyperbolic equation for hyperbolic diffusion random fields. So because of the solution of the hyperbolic diffusion equation is random initial condition. So this is not full class of spherical random fields on a sphere, but subclass of it. But for us, it will be enough to characterize so-called CMB data. Again, so how we are in three-dimensional space, X belongs, and then we consider restriction of this random fields Q of xt on a sphere. And that's our object of interest. And we denote this restriction on the sphere as to st h xt. So now x belongs to the sphere. And again, this is general form of restriction of the covariance function of the homogeneous isotropic random fields on the sphere and the sphere. I will, it's kind of combination of different places with different geodesic and spherical distances. And basically, again, covariance function of this spherical random fields now, which depends on time as well, is given by the green function of our equation. Fourier transforms this green function and spectral measure of initial condition. So J came from initial condition, and the rest from spectral theory. So again, using the theory which we already discussed, we can represent solution of this field TH on the sphere as spherical harmonics YL M of theta t and some random processes, stochastic processes, which are function of Lm of H and T. And this stochastic processes is given by this formula. So pi square root of T, J of L spherical, Bessel function of first order, and Fourier transform the given function, and that's a for initial condition, ZLM of d mu. Okay, now we are able to compute from this angular spectrum this random fields. So you remember that angular spectrum is defined as elements of the spectral decomposition of spherical random fields, and CL of t prime now is a function of t, is expectation of R LM of H LM of t of prime, and basically we can have explicit form of this form. So again, JL plus half over mu is V square is from spectral decomposition of isotropic random fields and homogeneous in three-dimensional space, H mu t and mu t prime from equation. So all equation now in this coefficient J is from initial condition. And as you remember, from H we have explicit representation in form of the three-dimensional, three-parametric Mehta-Claffer function. So it's complicated but explicit solution, which will help us in the future. So we can summarize now result as the following. So under the conditions, the spherical, fractional, hyperbolic diffusion random fields is isotropic random fields on the sphere with angular spectrum given by these two formulas. So that's the angular spectrum of this form. So now it's time to go to initial condition. What kind of initial condition we can consider? Of course, we can consider any initial conditions, but one initial condition especially popular in applications, so-called Mehta-Class covariance function. So if you consider such a covariance function of homogeneous isotropic random fields in three-dimensional case, where k nu is a modified Bessel function, such a covariance function known as Mehta-Class covariance function. And in this case, this spectral function is known explicitly for p mu square J of m, and J of m is known explicitly. So let us consider the partial case of the problem where initial condition is homogeneous isotropic random fields in three-dimensional space with specific covariance function called Mehta-Class covariance function or spectral density of this form. Well, just a popular example, let's say. Then basically we can now, we can now formulate this condition of for which theory works now, and basically, if you consider now partial cases for these partial cases, which can compute now this Fourier transform of the green function explicitly in form of the only one-dimensional, one-parametric Mehta-Claffer function. So again, you remember this formula. Now they are arrived in the different context, but in the same way. So we have here 1 plus omega. Omega was defined Mehta-Claffer function of I minus, which was defined t to the power alpha, and the same is plus, and so on. Again, here indicator of mu less than c over 2d and indicator of mu larger than c of td, which is typical for the theory of telegraph equations. So in this case, Fourier transform of the green function is much more simpler than it was three-parametric Mehta-Claffer function. Now it's one parametric. And again, Yes, this is a partial case when alpha equal 1, alpha plus beta is equal 2. This is also a new result. In this case, middle-class function and exponent, and basically we arrive to the kind of formula which is very classical for a Fourier transform of the green function of telegraph equation. So it's usually here such a formula. For those who know, it's not a new formula, but again, in this case, angular spectrum can be computed explicitly. So you see that angular spectrum CL for the Mattern class covariance function is given explicitly. Integral between 0 to C over 2D, Bessel functions, and all the other functions, which are functions defined explicitly. So basically, we're able to compute angular spectrum when initial value random fields is a Mattern class random fields. And now we arrive to the motivation, if you like. Maybe it was a good idea to start with this motivation. So there is a so-called famous CMB data, or cosmic ray background data. You can find about this data in in Wikipedia, because it's very what we know about, well, according to the Big Bang theory, or even without this Big Bang theory, that's what we have from the history of our universe. So we can build any theories, but at least that's a real observation of so-called microwave background radiation, and basically that's a spherical random fields. Well, of course, here there is a problem with isotropy, but people believe that we can assume a hypothesis of isotropy Gaussian random fields to this case. And basically, that's angular spectrum, which is function of L, of these random fields. And basically, this is well known, but so basically in this angular spectrum, there is a whole history of our universe, and for each monotone part there is a books. It was a beginning, then inflation period, and so on, how our universe was evolved to our stage of art now. And basically that's our angular spectrum, CL of TT, if C equal 1 and D equal 2. So that's basically, I mean, we use simulation of, so again, in the left-hand side is a real angular spectrum of CMB data. In the right-hand side is our simulated data through our angular spectrum, because we can simulate isotropic random fields and build angular spectrum according to our formula. So our formula are long but computable, and if t equal for some fixed t and for some fixed alpha, we can see that that's our angular spectrum. So you see that number of course, it's not exactly coincide with angular spectrum of CMB data, but number of peaks are the same, and there are some very big similarity of our angular spectrum with some parameters to angular spectrum of our real CMB data. So basically, again, we use simulation, and that's the references. The last part of the talk was published in the Journal Communication of Nonlinear Sciences and Numerical Simulation, and the first part in the Journal of Statistical Physics. And again, that was our motivation. So that's usually, that's simulated data over our homogeneous isotropic random fields with such angular spectrum. And that's angular spectrum. And again, left-hand side is empirical angular spectrum from the real data, and right-hand side is fractional solution of the fractional telegraph or diffusion hyperbolic equation on the sphere. And also one of the collaborator of our paper is Phil Broadbridge. He is physicist, and in this paper he produced some introduction, and he has some sort of explanation why for evolution of cosmic wave we need to assume that this is a fractional hyperbolic diffusion equation. So he produced hyperbolic diffusion equation, not fractional. But fractionalization of this equation gives us exactly similarity of angular spectrum because of because of otherwise we have something monotone which is not close to the angular spectrum. So sorry, I think I'm over time, and let me stop here. So again, let me summarize a little bit. We were able to compute explicit form of angular spectrum of a restriction of the homogeneous isotropic random fields with Mattern covariance function on the sphere. And then we would like to simulate, we were able to simulate these random fields because of that's a very simulation. Yes, sorry. So we can use simulation formula because of here is zeta are random variables. We can simply Gaussian random variables, and we can tractate and these integrals. And then we can compute the angular spectrum. And the result, we have such a similarity. So it was our motivation to study this problem, but not only. I think in general, generalization of hyperbolic equations on the sphere and spectral theory have more general interest than only to CMB data. But at least for CMB data, we have such results. Thank you.
Thank you very much for the nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen.
Yes.
I do not see any raised hands. So if somebody has a question, you can please unmute your mic and go ahead.
Maybe I ask if possible.
Yes, please.
Well, thank you, Nikolai. Very nice talk. I'd like to ask you what is actually particular S2 here, yeah? If I consider Sn or if I consider
S2
if
is
I
a sphere
consider
in
just
three-dimensional.
symmetric compact manifold
Yes,
with all
yes.
the variance, will it be the same more or less?
No. Okay. So, Vasily, thank you. It's a very deep question, actually. So, basically, the spectral, well, as I said, we were motivated by the CMB data at the beginning, but of course, spectral theory of random SISSA, what is written here, is known for much more general cases. First of all, we can consider not sphere of in three-dimensional space, but any hypersphere is n-dimensional space. In this case, we have some little differences from the theory. The only thing that instead of sum of L from 0 to infinity, the spectral theory where is here. Okay, LM, where is the first series of this? We will have, yes, this. So basically, these spectral numbers will be different. L will be from 0 to infinity, and M will be from 0 to so-called HML, which is given by different formulas. Here is 2L plus 1, but there is a formula how many we have orthogonal functions. In a sphere, we have not only 2L plus 1 in M, but more. And basically the same, but also, yes, the next question of Vasilius understood is why spherical harmonics. Yes, we can consider homogeneous spaces, and the solutions are known as Jacobi polynomials. And basically, again, we can potentially generalize more or less this theory in homogeneous spaces. So everything, the first part is doable definitely. And the second, because of, all this formula, there are analog of the any dimensions, not only three dimensions. But the second part is a little more sophisticated, but potentially also is doable. But again, yes, of course, it's not written. What is written now and published only in this form. Well, it's possible, but well, you have to do it because of many computations here, and of course, yeah. But potentially, yes, every formula known for both n-dimensional space, not as a sphere, hypersphere, and for homogeneous spaces with Jacobi polynomials as solution of the eigenvalue problems.
Okay, if somebody further has a question or a curiosity, you can please unmute your mic. Okay, I assume there are no further questions, so this is a good point to stop here. Thank you again, Professor Leonenko, to have you here. It was a really pleasure to host you today.
Okay, thank you for invitation again and for interest to this topic.
You're welcome.